Student will join in between. No issue.
Yes. I hand over this session to you.
Okay. Thank you, Dilpreet.
Thank
So
you.
let me start. Let me share my screen, and then we will start discussing the applications of linear algebra. So is my screen is visible to all, and my voice is clear to all?
Yes, sir. Everything is clear.
Okay. Thank you. Okay, so welcome to the third lecture of this TW on the linear algebra and its application. So in today's lecture, we are about to discuss the further applications of linear algebra in image processing. But today, today's lecture is going to be a little bit deviated from the image processing because image is again going to be a form of data. So in today's lecture, we are most likely going to discuss the data analysis or the application of linear algebra in in the data science in a broader sense. However, whenever your data is going to be the image data, then of course all the things are applicable to the image data as well. Okay, so let me have a very quick recap what we have done previously. So previously, uh, we have in the last lecture we have discussed about the single value decomposition. We have seen the algorithm for the single value decomposition, and then we have seen the two type of single value decomposition. One is called the full single value decomposition. Other one is called the reduced single value decomposition. And in fact in that lecture we mentioned that we are throughout this lecture series we are more concerned about the reduced SVD rather than uh, the full SVD, because the full SVD is not aligned with the philosophy or the motivation which we have for the factorization method, any of the factorization method. However, the reduced SVD is going to align with that particular philosophy. So we are sticking for the with the reduced SVD. Then we have seen the geometrical interpretation of SVD as well, and then finally we have seen the algorithm and done one example, which I think I have given a couple of homeworks to all of you, and I hope that you have done those small homeworks. So again, right now I'm not going to discuss that homework if you have some issues in that. So maybe after the end of this lecture, if you have some issues in those small homeworks, we will discuss those. Okay, so now the agenda of today's lecture is going to be as follows. So first we are going to discuss about the properties of SVD, which are very useful in diverse applications. Then we are going to discuss three applications of SVD today. One is called from the mathematical perspective. From the perspective of mathematics, and then that is called the pseudo inverse, where we are looking for the inverse of the rectangular matrices. Then the next two applications are basically from the data analysis, from the point of view of the data analysis or data science, whatever you want to say. And I am going to give the examples from the image processing. Just to elaborate, just to give you a brief idea of how the things are going to happen in this particular thing and how we are going to move it. And then maybe the later part of this lecture, we are going to discuss about the principal component analysis, which is going to be the ultimate point for this particular lecture series. And if time permits, then after this principal component analysis, I will give you the applications of linear algebra in diverse in diverse domains. So let us start our discussion on the single value decomposition. So I will take initial few minutes just review the algorithm for SVD, and then we will try to solve one more example, because the example which we have done in the last lecture, that is a square matrix. So you may not be able to appreciate the capability of SVD when we are applying it on A square image. However, you are going to appreciate SVD more when we are going to have uh, a rectangular image or a rectangular matrix on which we are going to apply the SVD. Okay, so let me quickly go for the algorithm. So the algorithm states such as or as follows. It says that given a matrix of m cross n. So now I'm just giving a very generic algorithm over here. So A may be real, A may be complex. If A is real, then this star will lead to transpose, otherwise it's going to be the conjugate transpose. So I'm going to have a general rectangular matrix A with me. Then the algorithm of SVD says that you have to identify A star A or A star, whatever is going to be have the smaller dimension you will pick it up. So I'm assuming that the smaller dimension is for A star A. So I will construct the matrix A star A. Then I will find out the eigenvalues and not the normalized eigenvector. So the length of eigenvector has to be 1. So we have to ensure that. So for this matrix, I am going to find out eigenvalues and corresponding normalized eigenvectors. So let's say the matrix of the eigenvalues is given by this particular matrix gamma, and then the eigenvector is going to be given by this V. So this is nothing but when you find out the eigenvalues, eigenvector is nothing but the eigen decomposition of the matrix A star A. After that, you have to sort the eigenvalues according to their magnitude, and then you have to construct the diagonal matrix sigma, which is going to be the matrix of the singular values by using the relationship which we have seen in the very last moment of the last class or last lecture, which says that sigma I or singular value is nothing but the square root of eigenvalues of A star A. So using this relation, we are going to find out the sigma. And then since the sigma is known, since V is known, then the only thing which you need to identify is U. Then we are going to use either this relation, this is a matrix representation of SVD, or the vector representation of SVD. So I'm just, I just rearrange the vector representation so that I'm going to give the proper definition of UJ. So you can use this one or you can use this one to find out the final matrix U. And as soon as you will get the matrix U, then you are having the matrix U, matrix sigma, as well as matrix V, and you are done with the singular value decomposition. So this is again going to be the algorithm for the reduced singular value decomposition. So this algorithm can easily be extended for the full singular value decomposition, because in that case you are looking for some extra vectors in any of U or V. So as long as you can induct different vectors which are going to be orthonormal in nature and going to be orthogonal with rest of the elements or rest of the element of this of the matrix U or V, then you are good to and you are going to have the full SVD of that particular matrix. So what I'm trying to show over here is, let's say in order to get the full SVD from R SVD, you need to add k columns in the matrix, let's say U. So depending on which matrix you have chosen, either you are going to get some additional columns in U or in V. So now let us take, so this is going to be a very hypothetical situation, then where I want to convert RSVD into the full SVD. Then in order to do that, I'm looking for k additional columns which are going to be cited in U. So what I'm going to do, what I have right now, so I'm going to have the column U1, the column U2 up to the column U1, and I'm looking for k more column so that I'm going to get the full dimension of the matrix U. So now you can add different matrices. You can on column U R plus 1, U R plus 2 up to U R plus k, such that U R, or maybe I will say U1. Okay, it's okay. U R plus I, the dot product between these two vectors is going to be 0, or the meaning is these are going to be orthogonal in nature, such and the length UR plus I is equal to 1 for all values of I. So as soon as you are able to identify these k vectors such that all those vectors are going to satisfy these two conditions with respect to all possible values of r as well as all possible values of I, then you are going to have the full singular value decomposition of that particular matrix A. So this algorithm which we are going to use for the reduced SVD can be used for the full SVD as well. So now, in order to do this kind of phenomena over here, or this kind of thing over here, we can always use the concept of the S-per, or you can say the perpendicular set of a particular space, and then you can do that. So, but again, it's going to be a very simple exercise for you, and you are going to induct multiple vectors into your matrix, either U or V, in order to make it a full SVD. And we know that the sigma, in order to get the sigma for the full SVD, it is just going to be a block matrix where you are going to have sigma in the left hand corner, and rest of the elements are going to be 0. And you can construct this matrix of desired sign to get the full SVD. So the same algorithm can be used for the reduced SVD as well as for the full SVD. For the full SVD, you need to find out these vectors so that you are going to achieve the full dimensions of matrix U and V. Okay, so now let us take a very simple example for SVD again in today's lecture. So now my question says that you have to find out the SVD of this matrix, and this is going to be a 3 cross 2 matrix, going to be a rectangular matrix. So again, the algorithm says you have to find out A transpose, because it's a real matrix. So the A star is going to be A transpose. So it is not going to make any sense. So I'm going to check A transpose A or A transpose whose dimension is going to be less. I'm going to take that particular matrix. And from the very simple analysis, I come to know that A transpose A is going to be of size 2 by 2, and A transpose is going to be of size 3 by 3. So for reduced SVD, I'm going to take this A transpose A and I will do the calculations. Okay, sorry. There is some issue with the animation anyways. So I can quickly find out A transpose A, and this comes out to be this particular matrix, which is going to have 9 in the diagonal and 8 in the off diagonal elements. So again, this is going to be a symmetric matrix. So now the next step says you have to find out the eigenvalues and the orthonormalized eigenvector. So if you are able to identify the characteristic equation of this, which is nothing but A star A minus lambda I mod is equal to 0. This is going to be the characteristic equation of this particular matrix. You can solve it. You are going to get 2 eigenvalues because the dimension of this matrix is 2 by 2. And when you solve that, you come to know that the first eigenvalue is 17 and the second eigenvalue is 1. So now you can simply solve the system A transpose A x is equal to lambda x, where lambda is going to be either lambda 1 or lambda 2, then x is going to be the corresponding eigenvectors. Just solve this particular system to get the eigenvectors. So immediately I can identify. So I'm not giving the mathematical calculation. I hope that you will be able to do the calculation. You have to find out the eigenvectors v1 and v2. So with respect to lambda 1 is 17, this is going to be my eigenvector, and with respect to lambda 2 is equal to 1, this is going to be my eigenvector v2. Now I am looking for orthonormalized eigenvector, and I come to know that the length of these two vectors are not 1. So then you will make these two vectors normal by dividing their length, and the length of both the vectors is going to be √2. So this the normalized version for this particular vector is going to be 1 by √2, 1 by √2, and for this is going to be 1 by √2 and minus 1 by √2. So now using these two vectors, you will be able to create the matrix V, because we have seen in the last lecture that whenever you are taking A transpose A, you will get V. Let me give a very quick proof of the same if you want to know. So I am looking for A transpose A. Let me say that A is equal to USV transpose, this is SVD of it. So I am going to get A transpose is nothing but USV transpose whole transpose USV Then I know that A B whole transpose is nothing but B transpose A transpose. So I'm going to get the V S, because it's a diagonal matrix, so the transpose of S is going to be S only, and U transpose U S V. You can combine these two matrices. Since U is orthogonal, it will go to I, and I'm going to have V S V transpose. So whenever you are going to take A transpose A, you are going to get V and sigma, and whenever you are going to take A transpose, you are going to get the U and sigma. So again, using the same analysis, you can immediately identify that whenever you are going to have the A transpose, you will get the matrix U and sigma. So using these eigenvectors, I can immediately construct the matrix V by stacking these eigenvectors as the column of it. And what is the order? Again, order will follow the order of the singular values, and I know that singular values is going to be in decreasing fashion. So the maximum eigenvalue is going to be there, then the lesser one, and then so on. So now from this lambda 1 and lambda 2, this is the bigger value. When you take the under root, this is again still going to be the small bigger value. So the first singular value is nothing but under root of 17, and the second singular value is going to be under root of 1 is going to be 1. So this is going to be my singular value matrix, and the eigenvector with respect to root 17 or 17 will go as a first column, and the second element will go, or second eigenvector will go to the second element. So this is going to be my V. So now I am having well-defined A with me, which is given to me, then well-defined sigma and well-defined B. Now the only thing remaining is the definition of U. So now the fourth step says find U. Either you can use the definition of SVD, since in the last example we have used the definition of SVD. So I intentionally choose the vector relation to find out the matrix U. So what is the benefit of this representation over the matrix? So in the matrix representation, you will use the matrix multiplication and you are going to get the complete U at once. However, over here, you can plug in the different values of J. Let's say you are going to have J is equal to 1 and 2 in this particular case. So you are going to have the V1 and V2. So with respect to the value of V1, you are going to get the U1. And whenever you are plug in the J is equal to 2, with respect to V2, you are going to get the U2. So it's all about, you will take one vector as input and you are going to get the one vector of your matrix U as the output. So it is like give and take kind of thing when you are giving an input of vector and you are getting another vector, and that vector is associated with matrix U. So let me quickly do that particular exercise. So using this particular formula, since sigma j is going to be a scalar value, so the inverse of that particular value is going to be just reciprocal to it. So u1 is nothing but 1 over sigma 1. Sigma 1 is root 17, which we have seen in the last slide. So it's going to be square root of 17. Then matrix A is given this. V1 I know that is going to be 1 by root 2, 1 by root 2. So you can plug in that, you can multiply everything, simplify everything, and you are going to get the first vector of u1 is going to be 1 by square root of 34, and the vector is going to be 3, 4, 3. In the same manner, I can immediately identify the vector u2 because v2 is also available. So in using the same concept or same formula, I am going to get the value of u2, which is going to be 1 by root 2 minus 1, 0, and 1. So after doing this, because now no more Vj is available, and hence the complete algorithm is going to be culminated. I am going to construct U by stacking these two vectors as a column of that particular matrix. So in that particular case, when I do that, then this particular vector will go here, and this vector will go here, and I'm going to get the matrix U for a given matrix A. So now I am going to have the definition of the proper definition of matrix U, matrix sigma, and matrix V. Now I only need to check when I multiply these three matrices in the form of U sigma V transpose, whether I am going to get A or not. If I am going to get A, then these factorization is perfect. So now you can easily verify that when you multiply these matrices in a certain form, you are going to get your given matrix A, and hence the SVD of matrix A is given by this U. This is my U, this is my sigma, and this is my going to be V transpose. Since V is going to be a symmetric matrix, so it doesn't matter V and V transpose, both are going to be same. So hence, in this particular manner, using these 4 steps, we are going to always find out the reduced SVD, and whenever you want to find out the full SVD, then in order to find out full SVD, what you have to do, this sigma in this particular case is going to be, the sigma is going to be root 17, 0, 0, 1, 0, and 0. So that this multiplication on right hand side with V transpose is going to be there, because it's going to be 3 by 2 and this is going to be 2 by 2. So V is going to have the full dimension. So I don't need to change V. However, in order to take this particular multiplication now, I am looking for U as 3 by 3. So in order to make the multiplication compatible, U has to be 3 by 3, so that this multiplication of U sigma is going to happen. So the meaning is I am looking for one additional vector over here. Additional vector going to be here, which will define the full SVD of this particular matrix. So now you can plug in any vector which is perpendicular to this vector, and whose length is going to be 1. So it is going to be very simple exercise for you. You can always find out a vector U3 such that U3 dot U1 is equal to 0, U3 dot U2 is equal to 0, and mode or the norm of U3, whatever you want to say, is going to be 1. So now you can plug in the U3 as, you can assume the U3 is going to be X, Y, and Z. Then you will get the one equation, X multiplied by this element 3X by square root of 34 plus 4X, or maybe simply I can give this value to you. It's going to be 3X plus 4Y plus 3Z is equal to 0. Similarly, with this relation, you will get another equation which says that minus X plus Z is equal to 0. And this relation will give me that X is equal to Z. When you plug in this value over here, what you will get? You will get, let me take everything in form of Z. So I am going to get 3 Z plus 4y plus 3z is equal to 0. I'm going to get a 6z plus 4y is equal to 0. So you can take any value of z such that you are going to get the value of x and y. So is this nothing? If I take z is equal to 1. So if I take z is equal to 1, then this vector u3, let me utilize this place. U3 is going to be what? X is z, so it is going to be 1. It is going to be 1, and this vector is what? By the value of y is going to be, from this equation it says y is equal to minus 6z by 4. So it's going to be minus 6 by 4. So now you need to check whether the length of this vector is going to be 1 or not. If it is not 1, just divide by the norm of u3. So your third element in u is going to be u divided by norm of u3. And when you include this with this new vector over here, you are going to get the full SVD of the same matrix A. So this is how the same algorithm can be used in order to find out the full SVD or the reduced SVD, whatever you want to obtain. But if you look at the from the application point of view, then of course the reduced SVD is more useful than the full SVD. So I hope that whatever calculation I have done in a very scattered manner in this particular slide, you will be able to understand that. So is there any issue regarding this, how the reduced SVD is going to be converted into the full SVD?
It is clear, sir. But can we use the cross product here, sir? Because of if we find the cross product of these two vectors, then that will be the perpendicular to both of them.
You can do that. So this is one of the way. So ultimately, at the end, when you plug in this value u3, you have to check whether this is going to be orthogonal or not. If it is not orthogonal, then you cannot use this new vector. Then you have to look for another vector. But anyhow, if you're going to follow this particular process, you are going to get an orthogonal matrix. But as long as this matrix is orthogonal, you can include different vectors over here, and different processes are going to be there. So this is one of them. So certainly you can use the other methods as well. So the only thing you need to understand is you have to have an orthogonal matrix over here. If you are violating that, then even this vector cannot go inside this particular matrix U. So let me give again that homework of today's lecture, that after including this vector into this, whether U is going to be orthogonal or not, you need to check. So check the orthogonality. So check, let me write over here, the orthogonality of this particular matrix U. Please check it. So, but this will give you an idea why U is not going to be unique in the full SVD, because now you are going to have the ample of what you say options available to create a orthogonal matrix U, which is going to have the full image. But again, the algorithm can be used, and then how to include this new vector. There are multiple ways to do that, and you can utilize all of your knowledge from the linear algebra and then or the matrix theory to do that. Okay, so this is all about SVD. So now let us quickly jump into the properties of SVD. Why SVD is so popular in diverse applications? So there are few properties of SVD which I am listing in the coming slides from the perspective of image processing. I'm not giving the very diverse all the properties of SVD, but I'm going to give a couple of properties of SVD which are very useful in at least in the image processing or the signal processing, and that is why SVD is having many application in these two domains. So the first thing, so the question is why SVD? The first property is going to be the transpose. Let's say you are going to have a matrix A with you, and you are going to take the transpose of this matrix A, that is A transpose. Then A and A transpose are going to have the same similar values. So now this particular property is very useful in image processing, because when you talk about the transpose, so transpose is nothing but a rotation with the angle of 90 degrees. So let me take a very simple example. So let me say this is going to be my given image A, and this is going to be my image A transpose. So now you can look at what you will do when you convert A to A transpose. I will take the first row and I will make it as the first column. So now this is going to be a horizontal line. This is going to be a vertical line. So now in these vectors or the rows and the vector or columns of these two matrices are related, that one vector is going to be rotated by 90%, 90 degree, then I am going to get the first column of another vector. So whenever from the image point of view, it's going to be rotation with a 90 degree of angle. So now this property of SVD will make SVD very useful whenever some intruder try to rotate the few objects of a particular image, so that you can identify what are the different objects. So it will actually not change the underlying properties of the given matrix A. So you can always go and check for the authenticity of those particular claims which some intruder is doing. So I have done this example in the MATLAB. So when I try to find out the singular value, then I'm going to get the singular value over here. So this is going to be a 8-bit 4x4 image which I have constructed in MATLAB, and then I am just giving the singular values of these two matrices, which I have again calculated from the MATLAB only. So now you can look at these two matrices are going to same, and hence the eigenvalues of this singular value of this matrix and this matrix is going to be same. Again, this is a very simple property, and it can be proved very easily using the relationship between A and A transpose, that you can do very easily. So I'm not going into the theoretical proof of this, but when you have the images, then the transpose is nothing but the rotation, and it is going to make your image or the process, you can say, resilient to the rotation with the 90 degree of angle. So this is one of the property. The second property is flip. The horizontal and vertical flip version of every real matrix A have the same non-zero singular values. So the flip means I am looking at the reflection either with respect to horizontal axis or with respect to the vertical axis. So now let me take this particular matrix again. This is going to be the same matrix A, and this is going to be the flipped version AF. Then these two particular matrices are going to be going to be same. Again, if I calculate these two matrices, if I again calculate these two matrices using the MATLAB, then I'm going to get the same singular values for these particular two matrices. Now the film is again again of the utmost important, because the flip is again is nothing but the rotation by 180 degree. So when you look at the reflection of anything, is going to be the rotation by the 180 degree, either the clockwise direction or the counterclockwise direction, depending on where you are going to in the first quadrant or the second quadrant, the third or fourth quadrant. So this SVD is somehow going to be resilient with respect to the rotation. That too, some of the specific angles only, but it is a very good property which can be utilized in the signal processing or the image processing applications. Okay, so now the third is the stability of the singular value decomposition. So the singular values of a matrix are having the very good stability. So what is the meaning of stability? The meaning of stability is, if I am going to introduce a little change in my matrix, then the singular values are not going to change a lot. So there is not going to be a very drastic change in the singular values of a matrix. So the singular values of a matrix is going to have a very good stability property, which can be utilized in numerous applications wherein the equilibrium is going to be of main thrust. Wherever you want to find out the non-changing positions or non-changing kind of thing or entity, then this particular SVT is going to perform very well in those applications. So let me take a very simple example. So that I'm going to take a very visual image for in order to show the stability, and then I'm going to have this particular image. So what I did is, I'm going to take this original image A, and I have added the uniform noise in this particular image to get this new version of A, that is called the corrupted image of A, let's say A bar. Then if I'm able to find out the singular values, then there has to be some difference because I'm changing some values. However, there is not going to be the drastic change. So if you're able to find out the singular values of A and A bar, then the highest singular value is going to be 32,036, and here I'm going to get 30,536. So now if you look at the difference, then difference is going to be low when compared to these when compared to the number which I'm going to have, or the you can say so basically in this particular scenario, what you are trying to do, you have to look at for an error tolerance. So as soon as that error tolerance is going to met, you are going to use this particular stability of the singular values of the particular or a particular matrix. So if I say that I can tolerate the error of 10 to the power 2, then this is not going to be a very good stability. The meaning is, now I need to get back, and then I am not going to introduce this much noise in my image. I have to introduce a little bit low noise. But if my error of tolerance is for 10 to the power 3, then it is going to be perfectly fine, because I am just getting the difference up to 10 to the power 3 in these particular numbers. So these are the only things which are going to be changed in these two particular numbers. And the similar kind of observation we are going to look at in the rest of the eigenvalues, singular values. However, the error tolerance which you are considering has to be obtained from the highest singular value of your matrices, because whenever you distort something, the effect of that distortion or the change is going to reflect maximum in the highest singular value, because this singular value is nothing but the average of the energy of the signal. In case this is going to be the matrix. So the maximum reflection of any change you are going to observe in the maximum singular value, and hence this error tolerance is with respect to the highest singular value rather than the lowest or any intermediate singular value. But the idea over here is, now you can look at the visual quality of these two images. So the visual quality is very good in this, and this though the image is visible, I can recognize the object. So I can recognize that there is going to be one person who is holding a camera with a tripod. But if you look at this background, small tiny part, the some of the details are completely gone. So I am losing the information, but still this SVD I am going to have a very less error tolerance of that particular in that particular case. And hence, depending on the application where you are going to use SVD, you can fix up your error tolerance, and with respect to that error tolerance, you can define the stability of that particular stability of the signal values in that particular application. So these are not the only three properties of SVD which are very important, but from the point of view of the image processing application, these are the three main properties which are frequently used in a number of applications. Let me name some of the applications. One is the multimedia security, when you are looking at the digital watermarking or maybe the image hashing. So these are the some of the areas where the SVD finds numerous attention of the research community because of these three main properties. But again, if you look at the mathematical properties, then you are going to have a long list of mathematical properties, which we are not going to discuss in this lecture. But you can get the book Matrix Computation by Ginny and Gaurav. So this is the book called Matrix Computation by Gaurav. So this is a very famous book and a very beautiful book in the matrix theory. And if you want to learn more about this SVD, please, I suggest you to go and consult with this book. This is one of the gem kind of book in the matrix theory. And you will find all the properties of singular value decomposition in this book, which is the Matrix Computations by Jenny M. Gaurav. So you can consult with this book, and if you find some issue, then we can again contact it over. I can contact it over the email. Okay, so this is all about why we have to use SVD. So I have given you the three reasons why we have to use the SVD. One is it is going to be resilient with respect to the rotation, with at least to some of the angles, and then the singular values are going to be going to have a very good stability when you are going to introduce the corruption in the matrix, or you are going to have a slight change in the entries of your matrix. Okay, so now in this particular slide, we will try to understand which is more important, singular values or singular vectors, because I know that now we are going to have two things. This any matrix can be decomposed or factorized in the three different matrices U, sigma, and V transpose. So whether the singular vectors are important or the singular values are important, that's the main question. Because the importance of these singular values and singular vectors will tell you in which application we have to go with the singular values and in which application we have to go for the singular vectors. So in order to explain this particular phenomena of the importance of singular values and singular vector, or you can say singular values versus singular vectors, let me take two images. So I'm taking two different images right now in front of you. Let me say this is going to be my image A and this is going to be my image B. So these are going to be two visually distinct images. And there is nothing common in these two images. So this is going to be a scene of, or you can say the photograph of a lady, and this is going to be a photograph of a person holding the camera. And this is going to be one lady maybe inside the house. So now, first we will do is we will decompose or factorize these two matrices or these two images into the corresponding, what you say, the US and V. So I'm going to get the UA sigma A VA transpose. So this is nothing but a singular value decomposition of A. Similarly, I am going for the singular decomposition of this particular matrix UB sigma B and the VB transpose. So now what I'm trying to do is, now I'm trying to do a mix and match. So I will choose this as my main image, and now I am trying to replace sigma A by sigma B and then try to see what will happen. Ideally, if sigma B is going to be of the utmost importance, then there has to be drastic change in my reconstructed image. So now I am going to take this new image, and this image I have constructed using the correct similar vectors or the wrong similar value. So again, all these experiments I have done in the MATLAB, so you can you can immediately go and do these kind of experiment. So whenever I replace just the similar values, there is going to be some distortion in the image. So there are going to be some error in the image. Like this is the error, then I'm going to have few error over here and few error. So there are some blocking artifacts coming into the picture. However, the quality of this picture is good and it is close to the original image A. And this experiment will tell me and intuitively tell me that the sigma A or the similar values is not that important for a matrix, because after changing the complete similar values vector matrix, I am going to get very less change in my reconstructed image. Now in the next experiment, what I did is I just tried to change the eigenvectors. So now this is going to be the same experiment which I have done for this matrix. So this is going to be UB sigma A VB transpose. Again, you can see that there are some artifacts over here, other texture points over here, over here. So there are some blocking artifacts coming over here. However, the reconstructed image is still close to the original image. So both the experiments are telling me that, okay, then this particular singular value matrix is not that important for a given matrix. You can still reconstruct your matrix with very less error when you are completely replacing your singular value matrix with some other matrix. Okay, so now the third experiment is, now I have changed the singular vector. So this is the image which I have constructed having the correct left singular vector, correct singular value matrix, and the wrong right singular vector. And if you do that, this is going to be the output. The meaning is the structure of the complete image is going to be destroyed. There is going to be a drastic change in my reconstructed image. Though I am going to get some overview of the image, like if I know the this is the original image, then I can make out that this is the face of a person and this is the code or something like that. However, if I show these two images, this image and this image, to a random human observer, then he may not be able to identify what is the correlation between these two images. And hence this experiment is saying, even after changing the singular vector of my matrix, I can completely destroy the orientation of the structure of my matrix. So there is going to be a drastic change in my matrix. So now I am going to do one more experiment when I am going to change both the singular vector. Let's see what will happen to the image. So now this is the image which I am going to get, which is UB sigma A, VB transpose. So in this case, I have taken the correct singular value matrix and the wrong singular vector matrices. So now you can see that now even I am going to get the more worse result when I am going to replace both the singular vectors. And hence this particular experiment shows that for a given matrix, the singular values are not important. And it is again going to be in line with our third property, which says the singular values are going to be stable. So this is the main reason why, since our singular values are stable, even if I change something in the singular value, it is not going to give the drastic change in the reconstructed image or the reconstructed matrix. However, since the eigenvectors are not stable and hence a single change in the singular vector will lead to the drastic change in the reconstructed matrix or the reconstructed image. And in essence, this sigma A will store the energy of the signal. Energy means L2 norm. L2 norm of this particular matrix. So you are going to have a matrix, and if you want to find out the L2 norm of that matrix, then using this particular sigma A, this L2 norm is going to be stored in that. And whenever you talk about the structure of the matrix, that is going to be stored in U and V essentially store the structure of the matrix. And hence, in general, we should not touch the eigenvectors of a matrix, otherwise it will lead to a drastic change in the matrix. And hence, singular vectors, maybe left or right, both are more important for the reconstruction of your matrix or the reconstruction of your image. And hence, in the fight between the singular values and singular vectors, singular vector actually won with a very high caution that you should not touch the singular vectors of a particular matrix. Let me take a 2-minute break and ask you if you have some query. Maybe you can talk to me right now. Otherwise, we will proceed further. So, any issues, any clarification you are looking at till now? It seems that there are no further queries. So let me proceed further and then continue our discussion on the singular value decomposition. Okay. So thank you, Vijay, for telling me that there are no doubts. So let me proceed further.
Sir,
Yes.
just one question. Sir, why this thing is happening means singular values are not affecting and singular vectors are any reason behind?
I mentioned that the main reason is the stability of the singular values, the third property which I have mentioned. So if you change something in your matrix, essentially you are changing the singular values. But there is not too much difference between the singular values, because if you look at that example which I have taken for the stability, visually both the images are distorted. Those are very far from each other. But their singular values are close to each other. So due to the stability of the singular values, the consequence is singular values are not that important for the reconstruction of a matrix. But if you change a single element to either of your V and U, then it is going to reflect as a drastic change in the reconstructed matrix. So this is all about all due to the stability of the singular
values. Okay,
yes.
Sir. Okay. Thank you, sir.
So now you have to decide whether you are going for the singular value or going for the singular vector, because there are some applications which do require the usage of singular vector, and if you are requiring the usage of singular vectors, then you should not touch those. If it is not requiring the usage of singular vector, then you can do anything with the singular vector. For example, let me give a very simple example to you that there are two, I have mentioned two application image processing. The first application is image watermarking, and then second is the image hashing. So the image watermarking, the reconstruction of the matrix is required, and hence we are not going to change U and V if we are using the SVD in the image watermarking. So no need to change anything. There has to be as perfect as possible. Image hashing, the reconstruction of the matrix is not required, and hence you can do whatever you want to do with the U and V. So let me quickly explain what is the meaning of image hashing. So image hashing is nothing but a function which will take some input. So you are going to have a matrix A, then out of this matrix you are going to get a vector or the feature vector which is going to be very robust against the different kind of you can say different kind of manipulation. Like someone want to distort this image, doesn't want to compress this image, someone want to add this particular some noise in this particular image. So these vectors should not change. So now you are more concerned about the stability. So in that case, there is no need of reversibility, because using a single vector you cannot construct a particular image. So the reconstruction is not a thrust point in this particular application of image hashing, and hence you can change your U, you can change your V, you can simply discard U and V. No issues in that. However, over here in this image processing, since I need to reconstruct our image at the end of the complete process, So I should have the access to the accurate UNV. Otherwise, it is going to create the distortion in the reconstructed image.
Okay.
Yeah. So again, it all depends in which application you are using the singular value decomposition. So different application is going to have the different moves with respect to the singular value decomposition. But the general thumb rule says do not distort your UNV. Otherwise, the structure of your matrix will go.
Okay, sir. Thank you, sir.
Okay. Okay, so in this slide, I am giving the very first application of the singular value decomposition, and that is called the pseudo inverse. So pseudo inverse is a mathematical way by which you can find out a inverse of a particular rectangular matrix. So any matrix A plus is said to be the pseudo inverse of the matrix A if these four conditions are satisfied. So if a matrix A, if you will be able to find out a matrix A plus which will satisfy these four conditions, then that A plus is called the pseudo inverse. And these four conditions are called the Murray-Penrose condition for the pseudo inverse. So now, given a matrix A, construct A plus will take a lot of time because it's going to be hit and try method. I will choose one A plus and then I will try to verify whether all four conditions are verified or not. If it is not, then I will leave that A plus and then I will pick another value of A plus and so on. So this is going to be a very time consuming task and it is going to take a lot of effort of yours to construct the A plus with respect to any given matrix A. However, the SVD is going to give you a very nice way to find out this particular pseudo inverse. So let me try to explain that in a very precise manner. So let's say for the time being, I am taking A as the square matrix, then we will extend it to the rectangular matrix. If A is a square matrix, then I can immediately give it to or factorize in U sigma V transpose. Now I am looking for inverse of this matrix. So I am saying that A is going to be an invertible matrix right now. So if I want to know the inverse of this, I will say A inverse is equal to U sigma V transpose whole inverse. I know that AB whole inverse is nothing but B inverse A inverse. So this is nothing but V transpose whole inverse sigma inverse U inverse. Is it clear to everyone? So now, what is the meaning of V transpose inverse? So I am looking for V inverse of V transpose, which is nothing but V, because V is going to be orthogonal. So say V transpose is equal to I, and this implies that V inverse is equal to V transpose, or V transpose inverse is equal to V. So V transpose inverse is nothing but V. This is going to be sigma inverse, and U inverse is nothing but U transpose. So if for a given matrix A, you will be able to identify U, V and sigma, then using these three matrices, you are going to find out the inverse of that particular matrix. So this is the scenario when my matrix A is invertible. Let's say my matrix A is not invertible. If it is not invertible, then this inverse, which I am going to get using this particular formula, is nothing but the pseudo inverse of that particular matrix A. So this is how in this particular manner we can immediately identify a pseudo inverse of any given matrix A. So whenever the matrix is invertible, then the pseudo inverse is equal to the actual inverse of that particular matrix. And if matrix A is not invertible, then this is something called pseudo inverse, and this A inverse or exact inverse doesn't exist for that particular matrix. So now you can assume any matrix over here, and for that particular matrix, you can easily identify the singular value decomposition. And as soon as you have the singular value decomposition, you can immediately identify the pseudo inverse of that particular matrix. So this SVD will also give you a way to find out the exact inverse of a matrix A if it is invertible. If it is not, you are going towards the pseudo inverse of that particular matrix. So this is the very you can say is going to be simplest application of SVD which you are going to use from the mathematical point of view, and you are now going to have the inverse of a rectangular matrix as well in the form of pseudo inverse. And the definition says you will find out U, sigma, and V. You will take V, you will take sigma inverse, and then you have to take U transpose. Multiply these three matrices, you are going to get the pseudo inverse. So this is going to be the foremost or the simplest application of SVD. Now let us go for the second matrix or the second application, which is going to be the noise removal. So now you are in this slide, you are looking at the two different images. This is going to be my original image A, and this is going to be the reconstructed image AR. So now you can look at, there are some difference over here. There are some block artifacts are coming over here. So let us try to understand what is the meaning of noise removal. So given a matrix A, I can add noise to it. It may be uniform noise, it may be no Gaussian noise, or it may be any other kind of noise. So if I add certain noise in my image, so let me add some uniform noise in this particular image, and I am going to get this particular image over here, which I am going to get over here. Now, if I try to take the SVD of this particular matrix, I am going to get something over here. So there are going to be only three non-zero singular values, and rest of the singular values are 0. So this is going to be 14.72. Now, after adding the uniform noise in this matrix, I am going to get a matrix something like this. So now objective is to reduce the effect of this noise from this image to get this image. So what is the way out? So now I am going to reconstruct this particular image, original image from this image, and then in the pursuit of that, I am going to get this particular image, which is again going to be noisy image, but the intensity of noise is much lesser when compared to this particular image. So now let us try to see what is happening over here. Since we have to reconstruct the image, as I mentioned in the previous slides, whenever you try to reconstruct your image, do not touch your UNV. So whatever, if I am going to use the SVD over here, then I am not going to change U and V of this particular matrix. Then the only option with me is I can play with sigma. So this is the sigma or the singular value for original matrix. Then I am going to find out the same for the corrupted matrix. So that is going to be this. Now you can look at, after adding the noise, I am going to get all the non-zero singular values. However, if you look at the first three singular values, so now the difference is going to be less. So again, you have to define error tolerance, and then you have to decide what to do. So now what I can do is I can assume a threshold T, and I will say that if the singular value is less than this threshold T, I am going to delete those elements and I am going to replace them with 0, and then try to reconstruct my image. So let's say if I take that T is equal to 0.6, let's say, then all the values which are going to be lesser than 0.6, I am going to replace by 0. So this will go to 0, and this will go to 0, and all the intermediate values are going to be 0. So now my new sigma n going to be this particular vector. So using this vector, I can always construct a diagonal matrix. This is going to give me the matrix for the similar values. Now I will use the same U and V and try to reconstruct my image. So I'm going to construct my image. A reconstructed is nothing but U sigma R V transpose. So what is the effect of the making them to 0? So because these elements, initially there are only 0 elements. So these non-zero elements are the effect of adding a noise in the image. Hence, whenever I'm making them to 0, essentially I am trying to reduce the effect of noise addition. So the reflection of this particular thing in this particular time is going to be something like this. So this is the result which I have constructed taking the threshold as 0.6. So all the values in this singular values matrix which are lesser than 0.6, I'm just making it to 0 and then try to reconstruct my signal. So now you can look at it. The intensity of the noise in this reconstructed image is less, and this image is more close to this original image when compared to this way. So this image is not close to the original image when compared to this image. So this particular phenomena is called the noise removal, and this is how we are going to remove certain amount of noise from the image or from the matrix. Of course, SVD cannot give you a perfect solution on noise removal, because at least whatever I have listed on in the this maximum signal value, that cannot be obtained by any means, and hence I can only do this. I can only do that. I can only reduce the effect of noise. That's it. So if I want to construct a far better result, then I need to go for the far versatile tool. Again, from the linear algebra, that is the Fourier transform, or maybe the wavelet transform, whatever you want to do. So these are the higher concept of the linear algebra only. So you can utilize those techniques, and then you are going to get the perfect result. However, SVD can be used. So the underlying idea says that the singular values that are less than a given threshold T, replaced by the 0 to suppress the noise in the image. So basically, it is not the noise removal, but it is the noise suppress. So you are just going to reduce the effect of the noise in the matrix. Now it will give you another application to it. If you look at this particular sigma, this will tell me that the rank of the original matrix A is going to be 3. However, in this case, I am going to get the rank of the matrix is greater than 3, is strictly greater than 3. In fact, it is going to be, in this case, it is going to be 25. The size of this matrix is going to be 25 by 46, and then I'm going to get the full rank, full row rank matrix after adding the noise. So this is going to be the greater than 3. So this particular effect will motivate researchers to think: can we use this SVD as the low rank approximation? Let's say I am going to have a big matrix that says that the rank is going to be more than 100 or more than 1 lakh. Can I reduce the rank of that particular matrix? So the next application of this particular signal value decomposition is the row rank approximation, and this is the SVD is going to be the best low rank approximation technique till date. So now let us say what will happen in the rank approximation. So let me take this particular image over here. So what I will do is, so this is going to be a matrix of 438 by 264. So this is the dimension of this matrix, and the rank of this matrix is going to be 264. This is going to be full column rank matrix. If you try to find out the rank of this image after converting into the matrix, you are going to get that rank of this matrix is 264, and the size is going to be given by this. So now, what the idea is, can I get a value k such that a new matrix AK is very close to the given matrix A. So now the objective of the rank approximation, you are able to construct AK which is approximately same as the given matrix, and this problem is called the rank approximation problem, because this K is going to be the rank of the new matrix. So basically, if the original matrix A is going to have rank R, then the new matrix is going to have a rank K, where K is a less number than R. So this is the whole problem of the rank approximation. So now let us try to do what will happen over here. Again, we are going to follow the same process which we have seen in the noise removal. I will convert my matrix A into SVD. Then I will pick the first K singular values, and rest of the values are going to be 0. So you just retain all the first K singular values, and remaining singular values replaced by 0, and then reconstruct your matrix A, that is going to be AK, and that is going to be the approximated version of the given matrix A. So let's say if I do this, I am going to get a sigma R, which is nothing but I am going to have the first K value same, and then rest of the values are going to be 0. So this is going to be K and this is going to be K. So this is going to be my new sigma when I put all singular values after K or first K singular values to 0, and then reconstruct my new image A K, which is a U sigma K V transpose. So this is nothing but the approximate version of A. So now let's try to see what is the effect of different Ks when I take a particular matrix which is given by this particular matrix. So now in this particular figure you are going to have the different images. So this is going to have the 2 rank approximation, the 2 approximate image of given image. Then this is going to be, I am going to retain that first 12 value. So the meaning is I am going to retain the rank of sigma as 12. This is for 22, this is for 52, and so on. So now you can look at it as long as you are going or traveling towards the actual rank which is given by this particular value over here, the quality of image is going to be enhance. However, I want you to look at this particular value. So what will happen over here? So now if you look at this image and this image, now using your eyes, you cannot tell me the difference. Hence, this is going to be the best approximation of this particular image having the rank of 112. So in order to store this image, I no need to look at the rank 264. I am going to look at the rank of 112. So the meaning is I am just trying to reduce the size of my matrix sigma, but I am not going to change U and V because I am going to require this for the reconstruction purposes. So this particular problem is called the rank approximation in the image processing, and where you just try to reduce the storage requirement for a matrix for a given matrix using the singular value decomposition. And this particular rank approximation in this particular sense is nothing but a compression technique. But it is going to be a very preliminary compression technique. For the actual storage requirement, you should look at the JPEG compression or the JPEG 2000 compression, which are going to be the latest and versatile technique for the image compression. However, whenever the data compression comes into the picture, still the rank approximation is going to be the best approximation technique for the compressing in journal data. So this is all about the 3 different applications which I want to discuss in today's lecture. Dipesh, I think there is a break for some time in between, or should I continue?
It is up to you, Gauravji. So we can also ask participants.
So all the participants, do you want some break, or should I continue? So anyone? Okay, so Shivani doesn't want break. Okay, anyone else? Okay, continue. So let me take a 2-minute time to just drink some water, then I will start.
Yes. Then we can finish early, maybe at 7.
It's okay. So my agenda is today to finish this principal component analysis. So now we will stop after finishing that only.
Okay.
But again, I think 1 hour is
stop for a minute so that just I change the streaming of YouTube.
Sure.
Streaming of YouTube, the 3 and 4 was different streaming platform. Means the link is different. So just change me. Just 1 minute it will take.
Okay, so we need to get out from the meeting, or it's okay?
No. Meeting will continue. Just 2 minutes.
Okay.